3, Black Hole and Orbits. Introduction. So the purposes of this lab were to calculate the mass of a black hole based off of a star's orbit around it. The second was to calculate the speed of some ship in order to successfully orbit a planet and its moon without crashing into or escaping from either. Both of these are based off of Newton's second law. The main result is that for part 1, we found that the black hole's mass was 5.85 times 10 to the 33rd kilograms. For part 2, it was that the ship should have an initial velocity of 26,500, 25,000 meters per second. So the physics ideas and equations are pretty much all based off of Newton's second law. We have the velocity and displacement update formulas that are derived from this law. Gravity formula, which is F grav is equal to negative G gravitational constant times mass 1 times mass 2 over distance squared times the unit vector of the distance vector. F net is going to equal dp over dt or F net perp plus F net parallel. The parallel and perpendicular components are going to represent the change in magnitude of momentum or the change in direction of momentum of some system. Assumptions, there's not really any assumptions that we're making. This is all theoretical computations. So everything we say is pretty much just the only thing that will affect our environment. There's no external factors that we don't know of that could affect our computations. For part 1 and part 2, the system of the star we're tracking, or for part 1, the system was the star, the surroundings was the black hole. For part 2, the system is the starship or the moon, and the surroundings is going to be the planet and the starship and the moon, but it depends on which one we're calculating for. So for the coding part 1, we know the star mass is going to be 2 times 10 to the 30th. That was given. Delta T is 86,400, which is time in a day in seconds. Momentum initial and velocity is just going to equal velocity, or momentum initial final will equal velocity initial final times mass, just by definition. Delta V and delta P will be final minus initial for them respectively by definition. dP over dt is going to be change in momentum over change in time, which is delta P over delta T. F net is equal to dP dt by definition over here by Newton's second law. P hat is the axis, so it's going to, or axis of parallel movement, which will equal the unit vector of the movement, which will equal momentum final unit vector. Then our dP dt parallel will equal that same axis parallel P hat times this magnitude of PF minus magnitude of PI over delta T, which is this line right here. F net power is equal to the dP dt power. Same thing, F net minus F parallel will equal F perp, which is what these two lines are saying. And then we can rearrange to solve for M2 for this F grav if we're taking the magnitude, which gets us this line, which will then result in our mass of our black hole. This code output, you can see here, I had to take the average of all the masses, or the mass of the black hole, to get an average of 5.85 times 10 to the 33rd. For coding part 2, here are the two velocities I was talking about earlier. To calculate the F gravity on the moon and on the ship, we just take the sum of the F gravities of the planet to the moon and the ship to the moon, and then the planet to the ship and the moon to the ship, and then we use these two position and velocity update formulas in order to find the moon velocity and position and ship velocity and position at every time step. Here we can see the code output. You can see the calculations finished after 700 hours. That means my ship never crashed into the moon nor the planet, and you can see that it was in the orbit of both of them because it didn't have a consistent like ellipse. It kept changing. So the errors, like the assumptions, we shouldn't really have any because it's all computational, all theoretical. The only error could possibly be me being wrong on some sort of equation, like setting it up incorrectly or using the wrong mass, but I don't think that's likely. So here are the whats. What does it mean? Well, net force and rate of change of momentum, I want to call it rate of change, are the same thing by Newton's second law. You can see it up here, but they are different in terms of calculating based off of observable facts, because net force is a lot harder to calculate than rate of change. For rate of change, all you have to look at is like a system's previous and current velocities in order to calculate that, or momentum. But for net force, you kind of need to know the system and its surroundings completely, because even random components from far away or really small components that you just didn't think about can affect the net force. So what if? So as we already have, we're going to need the black holes, stars, planets, moons, and ships' masses and current positions. We're going to need our formulas like net force, gravitational forces, velocity and position, update formulas, etc. We're going to need to maybe account for relativistic situations as well, so if something's traveling near the speed of light. and not everything would contribute equally. Something having a larger mass would affect everything else a lot more, like the black hole was a lot larger. Something being closer could also affect the surroundings a lot more than something really far away. So contributions will be very situational in terms of effects. And that's left there.